Okay, now that we have seen what happens when a current carrying conductor is placed in a magnetic field, and we get this motor principle, now we want to look at what happens when a charged particle moves through a magnetic field. It's not quite the same as a current in a wire. Charged, let's spell particle properly. When you're talking right at the same time, that's what happens. Charged particle moving through a magnetic field. All right. Well, if a conductor is moving through a magnetic field, we describe the force, the motor force, as Fm, the magnetic force, as BIL sine theta. Right? Right. Or if you're taking calculus and you know the notation of vectors, calculus and vectors, you could write this as I L cross B. Right? That is the same thing as this, and that'll make more sense once you get to your calculus. But here's how we're going to do it for now. This is how we do it, and this works out. It's all multiplying, so it works out great. Now, the problem is that there are two key things in here. The length of the conductor, which we said was this long. And the reason this is important is because the magnetic force is acting on every piece of this conductor, not just one spot. It doesn't just act here, but it acts here and here and here and here and here and here and here. So technically, it's acting at every spot along the length of this conductor, which is why we're multiplying everything by the length. And of course, the other thing that's in here is the current. And the current, of course, is simply how many amps of current are traveling through the wire. Okay. If we look at the idea of a simple charged particle, so what if instead of a current through a wire, we just had a single particle with a charge Q? And we'll call it a positive particle for now. So it's the same as the conventional current direction in the wire. And let's say it's just shooting through this space, but there's a magnetic field here. It's actually shooting through the magnetic field. Well, how would we describe the force on that charged particle? It's not quite the same. So we need to rethink this I and this L. We need to sort of figure out what does the length sort of relate to in terms of a moving particle. Well, you can see that, excuse me, if the particle is moving a certain distance, that could sort of be the length. The length could be considered how much the particle is moving, or the distance that it travels, which of course is speed times time, isn't it? And the current, so I'm going to write that over here. I'm going to write the length could be the same as the d, the distance traveled, which is speed times time. I know it's speed times time because it's constant speed, right? We're just assuming that this little charged particle is flying along without accelerating. All right. Now, you might say, well, if the force is affecting this little particle, then won't he be changing his path? And won't he actually be accelerating? Well, it turns out he will, and we'll see how he's going to move shortly. But what we're going to do is we're going to envision a very small amount of time. So that if we envision a very small amount of time, what we're doing is we're just basically breaking up this length into little tiny pieces of length. And what we want to know is sort of like, how much is the force at any little given spot. And of course, I can only draw these so small, but mathematically, we can make these pieces of length as small as we want. So it's almost like envisioning the force felt at each little spot along the conductor, along the length. So it's a fair assumption to make this little change. Now the other thing is the current. Current is defined to be the amount of charge moving through a conductor in a certain time. So N is the number of charges, and Q is the charge. So let's say you have a proton. One proton would be 1 N is 1, and the charge would be 1.6 times 10 to the negative 19. But if you had 20 protons, you'd simply multiply that by 20, and that would be the current. If 20 protons went past a certain point in a certain time, you'd get the current, right? Okay, well, what if we take this idea here and we replace the I in the formula with that, and we replace the L in the formula with this? What we would get is a new expression, and it would look like this. The magnetic force would be, I'll just move it down so you can see them both, B, but instead of current in a wire, we can equate that to a charge moving past a certain point in a certain time, so that becomes the current. And the length of the conductor is, in a sense, just how far the little charge has traveled, so Vt, and we get this. Now, what can we do with this? Well, right off the bat, you can see how we have a T and a T on the bottom, T on the top. They will cancel out. So this motive force could be written as B, N, Q, and V. But we're talking about one particle. So we already know that N equals 1. And so if N equals 1, then the motive force, or the magnetic force, on this particular particle would be B times 1 times Q times V. And the way we tend to write it in the textbooks for some reason is this way, QVB. That's the way it shows up. It's all the same, right? Multiplying. Oh, and I forgot something, didn't I? Didn't I forget something? I did. I forgot our little friend sine theta. Look at that. He has to be carried there too, because you see here he is up here. And I forgot about him. So if we add him into the picture, we get QVB, and then we have the little sine theta would be carried along with us. He'd still be here, he'd still be here, and of course, he would still be over here. So we want to make sure that the sine theta stays in there. And remember, the purpose of the sine theta is to make sure that we are multiplying by the part of B that is perpendicular to the movement of the per charge particle, to the velocity v. So that's what the sine theta is for. Now in a lot of the questions, it will be perpendicular already, and you'll just get sine theta, sine 90 is 1, and it doesn't appear very often. But you have to keep it there just in case you run into a situation where it might not be. All right? So let's look now at how this might appear. Now, let's draw a magnetic field. But I'm going to have to draw this in a funny way. I'm going to have to draw a magnetic field like this so you can see what happens to the particle. So what this is our magnetic field lines, sort of in cross section, sliced off, and they are running in and out of your screen. And we're going to make sure that the direction, we're going to say the direction here is coming out towards you. So the little dot means that this represents magnetic field lines, or arrows, coming straight at you. So it's kind of like if you drew this picture, right? And the magnetic field lines were going up. And then you took this picture and you took this top part and you bent it towards you out of the screen somehow. And all those arrows were now pointing directly at your head. It would sort of look something like I've drawn over here. Okay? All right. Now what we're going to do is we're going to take a little charge, say a positive charge, called Q. And we're going to put him right here, Q. I'll put him right here, positive Q. And he's going to move into this field. Now, as soon as he hits this field, we have a right-hand rule happening, don't we? Now, this right-hand rule is hard to draw. I don't know if I can draw a right hand like this, but I'll give it a try. What you basically have is your 4 fingers pointing straight at you of your right hand. And then your thumb is sort of sticking out this way. Okay? And that's sort of, and the palm of your hand is sort of down here. So very difficult to actually draw that. It would kind of look something like this, I suppose. Okay? So these are your fingertips pointing straight towards you and your thumb out that way. Now your fingertips are pointing in the same direction as the magnetic field lines, the red circles coming towards you. But your thumb is pointing in the same direction as the positive charge is moving. And so that means that the force would be the direction of your palm which would be down. So my right hand tells me that if a positive charge moves into this field, it will feel a force downward. So as soon as it enters the field, all of a sudden now I'm going to write that there's this force here, pulling down. Well, what is that going to do? Well, it's going to cause the direction to change. It's not going to speed the particle up, because the particle is moving to the right and the force is perpendicular. So it's not going to make the particle go any faster, which is weird, right? Because F equals ma. It's supposed to cause acceleration. But you'll see what kind of acceleration it causes in just a moment. It's going to pull this thing down, and so now it's going to turn in its path, and now it's moving this way. Now, because it's changed its direction, guess what I have to do? I have to change my right-hand rule. Here's my right hand again, fingers, and my palm now is pointing this way. See how my thumb has to follow the direction of the particle. So now this force is sort of pushing in this way. And that force is going to continue to cause this thing to turn. And so what's going to happen as I go around is you will see something like this. And then, of course, I'm running out of field here, so as I leave the field, and then I just kind of shoot off. But while I'm in the field, you can see that the force is all pulling towards the center of a curve, or the center of this curvature, which means that the force is actually centripetal. It's a centripetal force, and what this force causes is not an acceleration in velocity as such, but it does cause a change in velocity. So it causes a change where the speed remains constant around the circle, but the acceleration is towards the center. And it's exactly the same as if you took a string and a rock or a block and you spun it around your head in a circle, right? The tension of the string pulls in and we get centripetal motion. The only difference is now, instead of a string, we have this magical magnetic force caused by the motor principle. But it acts just like the centripetal force of a string might. And so now we know that this force is centripetal. Now, why would that be important? Well, that would be important because of what I'm going to show you right now. What we're basically saying is while this charged particle is in the magnetic field, it experiences a net force, which is the magnetic force. There are no other forces acting on it. Not significantly. I suppose you could say gravity is acting, but because it's such a tiny particle, the gravity is insignificant here. And the motion of this particle is mainly determined by the magnetic force in this field. Now, we just finished saying that the magnetic force was equal to Q V B sine theta. And we also said that the F net is a centripetal force. So this is a centripetal force, which means that mv squared over r, that's the formula for centripetal force, equals qvb sine theta. And this little expression then can be simplified, right? The first thing we can do is divide both sides by v. So we would get mv over r equals q b sine theta. And then, of course, we could multiply the r to the other side. Basically, we can do whatever we want. Let's do that. mv equals r times q times b. And if we make the assumption that theta will always be 90 degrees, we're always going to enter the field. Let's go back here to our picture. If you think about this picture, even if I enter from any direction, if I enter this way, or this way, or this way, because I'm entering on the plane of the screen, and because the red magnetic field is coming out of the screen, all of these lines are perpendicular to it, no matter which direction I come in. So that means that if we assume that sine theta, or theta is 90, then sine theta is 1 and it disappears, right? Sine theta is 1. So now I have this interesting little equation. And what I can do is I can use it to figure out, for instance, what the mass of a particle might be. Or if I want, I can figure out what the radius of the curve would be, mv over qb. I think in your textbook, this is the way they like to write this equation. But what's interesting about it is by looking at the path of the particle, we can tell lots of cool things. So for instance, here's the radius of the curve, right? So if I was looking at this particle, and I could take my ruler and measure how far that was, I would know the value of r. And if I knew a little bit more about the particle involved, like say its charge and its velocity, I could find out how massive it was. Or if I knew how massive it was, I could find out its velocity or its charge. And so why is this useful? Well, it's useful because around the turn of the century, we began to smash atoms together. We would hurl atoms together in particle accelerators. And when we did, tons of junk erupted out of the collision. And we got excited because scientists love to categorize things. So we started looking at all the pieces of junk, and we wanted to find out how we could put them in piles, right? So, I mean, we could have picked all the orange things in one pile or all the little round things in another pile. But there are certain criteria that we look for in particles. We want to know not what color they are or what shape they are, but we're more concerned about, for instance, how massive they are. Mass is a very important thing. We're also concerned about what charge they might have. That's a very important thing. And so you see how we could use this equation if only we could find a way to actually watch which way they went. Well, here's what we do. We take a special liquid in a chamber. When these tiny particles move through the liquid, they move through it, and they're microscopically small. In fact, they're smaller than microscopic. Even a microscope can't see them. So you can't just watch. If you were watching, this is what you would see. Nothing. But imagine if you're in a plane high above the ocean, and you look down in the water, I'll draw this in blue, and you see this weird sort of pattern like this in the water. And there are waves, and it's like a disturbance, right? We call this a wake. And you would say, gee, you know what? I bet you there's a boat right up there at the top of that wake. Even though I'm too high up and I can't see the boat, I know there's a boat there because I can see what the boat has done to the ocean behind it, which is now a great big spread out bunch of waves. And I suppose if you spent all your life studying different wakes and different patterns of disturbances behind boats, then you could say to somebody, oh, you know what? I know what's there. That's a Sidhu right there at that spot. And they'd say, well, how do you know that? Well, because I studied the wake of a Sidhu, and this looks exactly like it. Or maybe it's a different wake. Maybe it's longer, and it's got different wave patterns. You go, oh, I know what that is. That's a tanker. Yeah, that's a tanker carrying crude oil. How do you know that? Well, because of the wake. But you'd have to be an expert, and you have to study all the wakes. Well, guess what we do? These particles, when they stream through this magic liquid that we use, they actually interact with it in such a way as to produce tiny bubbles. And the bubbles make a trail that show exactly where they've been. And these bubbles are big enough to be seen, at least with a microscope, or a lens of some kind, or sometimes even with the naked eye. And so these trails of bubbles, guess what this is called? It's called a bubble chamber, right? And in fact, now we have even more sophisticated ways of doing this. We don't actually have actual bubbles, but we can find other ways of making tracks. But this was the original way, so I'm telling you about that. So now, here's what you do. I'm going to redraw the picture. You take atoms that you want to smash together, and you put them in a bubble chamber so that now their paths are visible. And if you take these two atoms, like this one, and you smash it together with the other one, like this, bam, what you will find is you'll get a lot of junk that you could see now. You'll be able to see the paths of the junk. But the other thing we do is we put the whole thing in a giant magnetic field. Aha! A giant magnetic field. And I'm just going to draw this magnetic field like this. And let's put a dot. Let's say that this is a magnetic field that's coming towards you out of the page. Unfortunately, some of my circles are too small, but it's coming towards you out of the page, right? So what will happen is, if there's a piece of junk that has no charge, it will fly off in a straight line. It won't be affected by the magnetic field because it's not charged. There is no motor principle here. And so some of the pieces of junk will make little tracks that are straight. But if I have a positively charged object, it will be affected by the magnetic field. The motor principle will produce that curvy path that we were talking about. So if I use my right hand and I have, let's say I have a particle that shoots off this way, well, immediately, because of the right hand rule, it will be forced to curve, if it's a positive object that is, it will be forced to curve in a spiral shape this way. Or if it's a negative object, I would have to use my left hand rule, right? Negative charge works in the opposite way, so you use the same rules with your left hand, and then you would get that picture. All right, so let's now think about a negative charged object. Let's say it begins to shoot this way, but with the left hand, using the left hand rule, it would curve in a path like this. And so we can see how one kind of object curves clockwise, the other curves counterclockwise. So by looking at the path, we can tell if an object is positive or negative, right? Actually, I drew that in purple, but that's the same as the blue one. That would be a negatively charged object, wouldn't it? So we can look at these tracks and we can tell what kind of charge is on our piece of junk. And we can also use other things, like for instance, if I take my ruler, because we can see this picture, right? And I measure the radius of this curvature, then I can find out about the mass of an object. I can also use the rules of momentum, M1, V1. Remember momentum? And the rules of momentum apply, and I can figure out stuff about the straight lines as well as the curved lines. And using all of this, we have been able to create a giant inventory of atom junk. And what we've done is we've described all these so-called pieces of atoms, these particles, and we have described their mass and their charge, their angular momentum, and something called their spin, and all these things, and we put them into categories. And that has formed the basis of what we call the standard model for physics. And it's one of the crowning achievements of the previous century, from 1900 until now. And so you can see how what we've learned here is the beginnings of how these scientists actually did their work and discovered these amazing things. A lot of these particles are not stable, so they don't last very long. Sometimes the track goes like this, and then it disappears because the particle has vanished. It's not a stable particle that can hold together long enough, and it vanishes into energy, basically. Sometimes you'll see a particle, right? You'll see something come shooting off, and then it'll break into two more things, and one will go this way, and one will go that way, and you see all kinds of cool things. And so the scientists can use these patterns, and they can use the mathematics that we've just used back up here to describe a charge moving in a magnetic field, and we can derive these equations to help us figure this out. And so here we have touched upon the beginnings of modern physics. We've used some of the classical physics rules, and we are now into the realm of modern physics, and it only gets way more exciting from here. Plus, the pictures look really cool. If you look at this one, looks like a really bad accident. But anyway, in that sense, that's exactly what it is. It's a really bad accident, right? Two atoms colliding together. But basically, what you need to remember here is that the force, the magnetic force, on a charged object moving through a magnetic field can be described as Q, V, B, sine theta. Or for the calculus people, you would write it as QV cross B, right? But this is how we will do it, because we haven't got that much calculus under our belts yet. QVB sine theta. And then, of course, you could modify that into this little equation up here if you wanted to find out something about the particles. And I believe this is the form the textbook uses, but you could write it in any form, right? It doesn't really matter which way you wrote it. So two kind of new equations for you to throw into your toolbox. And that's the end of that one.